All right, let's talk about an element that is, and I mean this literally, all around you right now. It's the silent, invisible majority in every single breath you take. But here's the thing, it's also strangely distant, a key ingredient for life that plays really, really hard to get. We are talking, of course, about nitrogen.
Just think about the air in the room with you. Almost 4 out of every 5 molecules floating around are nitrogen. That's a staggering 78%. It completely dwarfs oxygen, which, we think is so important, but it only makes up about 21%. So yeah, by a huge margin, nitrogen is the most common gas in our atmosphere.
And just to put that 78% into perspective, try to wrap your head around this number. Hovering over every single square mile of our planet are more than 20 million tons of nitrogen. It's just an unbelievably vast and constant presence.
And that right there brings us to the central paradox, the big mystery of this whole thing. We know nitrogen is a key part of our proteins, our DNA. It's absolutely essential for all life. So, if we are literally swimming in an ocean of it, why can't most living things, including us, just grab it from the air and use it? Well, that's the puzzle we're about to solve.
You see, the answer has nothing to do with how much of it there is. It's all about the chemistry. The secret to nitrogen's kind of standoffish nature lies right at the molecular level in one incredibly powerful connection. And this is it. This is the hero, or maybe the villain, of our story. In the air, nitrogen hangs out as 2 atoms bonded together. We call that molecule N2. But see that little symbol with the 3 lines in the middle? That's the key to everything. That is a triple bond. So what does a triple bond actually mean? Well, think of it like molecular superglue. It is one of the strongest bonds in all of chemistry, and it locks those 2 nitrogen atoms together with just immense force. And because of that, the N2 molecule is incredibly stable. And more importantly, it's super unreactive. It just doesn't want to play with anything else. To really get it, just think about oxygen. We all know oxygen is reactive, right? It's what causes things to rust, it's what fuels fires. Well, nitrogen, thanks to that powerful triple bond, is the complete opposite. Its whole personality is being inactive, which is exactly why we can breathe it in and out all day, every day, and it doesn't do a thing to us.
So, the big question is, if that bond is so incredibly strong, how in the world does life get the nitrogen it needs to build itself? Well, the story of life is, in a lot of ways, the story of finding really clever ways to break that bond.
And this whole process actually has a name. It's called nitrogen fixation. It's that crucial, all-important step of taking the unusable, unreactive N2 from the atmosphere and turning it into chemicals that plants and animals can actually absorb and put to work, like ammonia.
So who are the heroes that can pull off this amazing chemical trick? Well, nature has 2 main solutions. The first is just pure brute force. The massive energy of a lightning strike can literally rip that N2 molecule apart. But the real everyday workhorses, they're tiny microorganisms in the soil that use these special enzymes. Think of them as nature's own microscopic toolkits to gently get the job done. And let's be really clear here, this isn't just some neat little chemistry fact. These fixers, the lightning and the microbes, are the foundation of pretty much every ecosystem on Earth. They take this inert gas that fills our sky and transform it into the very building blocks of life itself. Without them, life as we know it just wouldn't be here. Okay, so life figured out a way. But what about us humans? Well, we've also learned how to harness nitrogen's unique properties, especially its unreactive nature, for some pretty amazing technologies.
We've essentially learned to do what nature does, but on a massive industrial scale. We figured out how to make ammonia, which became the starting point for fertilizers that now feed billions of people. We also use nitrogen's inertness to our advantage, pumping it into bags of chips and other food packages to keep them fresh. And of course, as a liquid, its incredibly low boiling point makes it a perfect and cheap cryogenic coolant.
But what happens when you finally break that triple bond and convince nitrogen to pair up with other elements, like oxygen? Well, that's when you unlock a completely different personality, one that's way more reactive and sometimes way more dangerous.
And the variety you get here is just fascinating. Once you get it to bond with oxygen, nitrogen forms this whole family of compounds called nitrogen oxides. You've got nitrous oxide, or N2O, which you might know better as laughing gas from the dentist. Then there's nitric oxide and nitrogen dioxide, which are both common air pollutants that create that ugly brown haze you sometimes see in smog.
And this is where nitrogen's personality takes a really dark turn. This quote is a direct warning from our source material about what happens when you heat a compound called ammonium nitrate. You see, while nitrogen gas is super stable, some of its compounds are the exact opposite. They're incredibly unstable and just packed with energy waiting to be released.
And this isn't just some lab experiment gone wrong. The explosive power of ammonium nitrate has led to absolutely devastating industrial accidents, like the ones in Texas City and West Texas. In fact, over the last 100 years, there have been nearly 30 similar disasters all around the world. It just shows you the immense power that's locked away in these nitrogen compounds.
So, it all comes down to these two faces of nitrogen. On one hand, you have the N2 molecule floating around in our atmosphere. It's stable, it's unreactive, and it's the quiet foundation of all life. But on the other hand, once you force it into compounds, it becomes this reactive, versatile element that gives us everything from life-saving anesthetics and fertilizers to deadly pollutants and powerful explosives.
Which leaves us with one final question to think about. Is nitrogen a quiet, stable guardian of our planet? Or is it a hidden threat, with all its power waiting to be unlocked for good or for ill? The truth, as we've seen, is that it's somehow, paradoxically, both.